Hi everyone! In this video we're going to go over epoxides. So the first thing I wanted to go over was how to name epoxides. So there are some common names for epoxides. So the one we're most familiar with is this three-membered ring where oxygen is at one of the corners of this triangle here. This is called oxirane. I think I'm pronouncing that right. It's always hard to tell in chemistry. Um, so we're used to this one, but you can have other epoxides as well. You could have a four-membered ring. This would be called oxetane. You could add one more carbon in that ring and it becomes oxolane. And then you can add even one more carbon to make a six-membered ring, and this becomes oxane. All right, so what if we have substituents coming off of our epoxide? How do we name the epoxide? Well, let's look at an example, and this is actually from your textbook. So let's say we have our epoxide with two ethyl groups on the left and two methyl groups on the right. One way to name this is to find the parent chain, so the longest carbon chain, and we want to make sure that the epoxide is attached to the longest carbon chain. So we're kind of treating the epoxide as a substituent. Oops. So we also want to make sure that the epoxide has the lowest number possible. So I'm going to number from right to left. Okay, so our longest carbon chain is pentane. So we'll write that down. And again, I'm using ANE at the end because we have all single bonds across that carbon chain. Then we're going to treat the epoxide as a substituent, and we're going to call it epoxy. And this epoxy group is in between carbons 2 and 3. Okay, so far we have 2,3-epoxy pentane. All right, and then we also have an ethyl group and a methyl group as our other two substituents. So now we're going to list those and their locations, and then we're also going to alphabetize them. So let's see, we have 2-methyl and 3-ethyl. And again, I made sure that ethyl was before methyl. But notice that I didn't alphabetize the epoxy substituent, so that went right before the carbon chain. Now, there is another way that we could name this molecule. We could refer to the epoxide ring where oxygen is at position 1, and then we just number around the ring. So we would refer to that ring as oxirane, which we saw above. Oxirane, I don't know. And then we just list where the substituents are on that ring. So we have 2 methyl groups on carbon 3. So we would write 3,3-dimethyl. And then we have 2 ethyl groups on carbon 2. So that's 2,2-diethyl. All right, so there's 2 methods again to name epoxides. Whichever one you prefer, you can use. Okay, so now let's talk about the reactivity of epoxides. Oh, I forgot to add reactivity here. Okay, so remember that to make an epoxide, we need an alkene. And let's just say this one has all hydrogens attached. And then we would use something like MCPBA, and that would give us our epoxide. Okay. Now, one thing to keep in mind when we're looking at this structure for the epoxide, what is the hybridization of one of those carbons in the ring? Is it sp, sp2, or sp3 hybridized? So remember, it is bonded to two hydrogens. So it is bonded to 4 different things. So its steric number is 4. So it is sp3 hybridized. And what are the bond angles between sp3 orbitals? 109.5. So that's the tetrahedral angle that we would expect. However, notice our carbon is bonded to another carbon and the oxygen up above in a triangle. And what is the angle there in the corner of the triangle? Might have to think about geometry for a second. 60 degrees. That is way less than 109.5. So if you have angles that are much smaller than what you would expect, we call that ring strain. So epoxides are actually super reactive because of that ring strain. The carbon atom and its bonds would prefer to have 109.5 degrees between them, but they're stuck at 60 degrees. So epoxides are very reactive due to ring strain. So if a nucleophile comes in, for instance, and attacks one of those carbons, that's going to cause the ring to open up, and it will open very easily because that will alleviate the ring strain. All right, so let's talk about the reagents we use to make epoxides. So remember, there are a couple of reagents we can use with an alkene to make an epoxide. So we could use MCPBA like we saw before, or peroxyacetic acid. And then we would get our epoxide. But before we draw our epoxide, let's show what these two different reagents look like. All right, so this is MCPBA, which remember stands for meta-chloroperoxybenzoic acid, MCPBA. Or again, we could use peroxyacetic acid, which looks like that. Okay, so now what do we expect our product to look like? So as we saw earlier, we're going to add an epoxide across that double bond. So an oxygen is bonding to both carbons across the double bond. But what do we do with those methyl groups? How do we draw those? Well, they're cis to each other. They're on the same side of that double bond. So when we draw the epoxide, we could show them as both being forward in wedges, although I can't draw this wedge apparently. Let's redraw that. Or you could show them as both dashes, as long as they're on the same side. So again, this is our epoxide. Now, you could also show the hydrogens if you want. So the hydrogens are also cis to each other, so we could show those as both being behind the plane of the bond. All right, so now let's talk about another way that we could prepare an epoxide. So this is epoxide preparation via Halohydrin reaction. So recall that if you have an alkene, we'll use the same one we saw before, and you treat it with bromine and water, you're going to see anti-addition of bromine, and water. And eventually you'll deprotonate the water group and end up with an alcohol. And then you'll also form the enantiomer of this as well. Okay, so that does not look like an epoxide, right? So in the next step, what we're going to do is add sodium hydroxide. And the hydroxide is going to deprotonate our alcohol group, and electrons will be left behind on oxygen. So now oxygen will be negatively charged, and this will also occur with the enantiomer as well. Now, one thing to notice in this situation is that the negatively charged oxygen is a good nucleophile, and bromine is a good leaving group. So what we'll find here is a substitution reaction, and it's actually called intramolecular. So we have an intramolecular SN2 reaction. So oxygen's going to attack the partial positive carbon bonded to bromine, and then bromine is going to leave because it's a good leaving group. And let's just write down intramolecular SN2 reaction, just so we remember what that's called there. So what you end up with is, I meant to draw that at more of an angle. You end up with your epoxide, and because oxygen was behind the plane of the paper, we're going to show the epoxide as being behind the plane of the paper. And you still have that enantiomer as well, plus a bromide ion at the end. So again, this is another way that you can make an epoxide. So if you were trying to use this reaction, what you could do with your arrow, if you just wanted to go straight to the epoxide, just write Br2H2O NaOH. So that will take you from your alkene straight to the epoxide. Okay. So let's do a practice problem. Let's say we have the following starting material. And let's say we treat this with MCPBA. What product or products would we expect? And feel free to pause the video and try this on your own first, and then we'll go over it together. Okay, so let's see what we get here. So I'm going to draw my epoxide. Okay, and then let me look at my substituents here and see what cis to each other. So it looks like our methyl group and ethyl group are cis to each other. And then this cyclohexane group and hydrogen are cis to each other. So I'm just arbitrarily going to pick my methyl and ethyl group to be in dash positions. So they're kind of going behind the plane of the paper. So that means my cyclohexane substituent is coming out in front, and my hydrogen is also coming out in front, so they're cis to each other. Now, the epoxide, the oxygen, could come from the top or the bottom of the alkene. So let's make a note. Oxygen can add top or bottom. So we would also see kind of the upside down version. And I'm still going to keep my cyclohexane and hydrogen groups as wedges and my methyl and ethyl groups as dashes. Okay, now what is the relationship between these two products? Are they constitutional isomers, enantiomers, or diastereomers? They're enantiomers. So both stereocenters, so the left and right hand carbons, they changed when the oxygen flipped from top to bottom. So with both stereocenters being different, that means we have enantiomers. Now, unfortunately, we have no control over which enantiomer forms. So this presents a problem. So how can we control the enantiomer that forms? How can we form one enantiomer over another? Well, luckily, a scientist by the name of K. Barry Sharpless, he came up with a method to preferentially form one enantiomer over another. And he actually won the Nobel Prize in 2001 for his work. So the overall process here is called Enantioselective Epoxidation. So we're creating an epoxide in a very specific way. So we're selecting a particular enantiomer, if you want to think of it that way. All right, so again, this was developed by K. Barry Sharpless. And he won the 2001 Nobel Prize for this work. So what Sharpless came up with was if you had a chiral catalyst, then that would help to form one enantiomer over another. So let's say you have an alkene. In this particular epoxidation reaction, you have to have an allylic alcohol. So remember, if you have a carbon one bond away from a pi bond, that is called an allylic carbon. And if you have an alcohol bonded to that carbon, it's called an allylic alcohol. So that is one limitation of this method, is you do have to have that allylic alcohol there for this to work. But basically, what you can do is use a peroxide, and then you're going to also use something called titanium tetraisopropoxide. So don't worry too much about these reagents and their names, but basically you have an OC-CH3 group, 4 of those, excuse me. Oops, I drew that wrong. That should be a 2. But you have 4 of those bonded to a titanium atom in the middle. So it kind of looks like, let's see, this. And then you also combine that with either plus DET or minus DET. And DET stands for diethyl tartrate. So let's draw that down below. Okay, so this will end up forming our epoxide with a very specific stereocenter where that alcohol is bonded. And that will form at about 99% enantiomeric excess. So you do still form a little bit of the other enantiomer, but it's so small that it doesn't really matter. And then again, if you wanted the other product where the epoxide forms the other enantiomer here, then you use the same reagents that we used up above. Except you use minus DET. So in minus DET, the OH groups down below would be in dashes instead of wedges. Now, you don't have to know the mechanism for this. Just be aware that you can select or choose one enantiomer over the other if you use one of these enantiomeric catalysts. Now, luckily, since this was developed, other scientists have been able to come up with other catalysts where you don't have to use an allylic alcohol. You could just use any alkene, which is nice. So, just something to be aware of, that you can perform this type of reaction without the allylic alcohol too. All right, so I think we'll stop there for this video. In the next one, we'll talk about ring opening of epoxides. And then we're also going to talk a little bit about acidic versus basic conditions with epoxides, because the acidity of your solution does affect your reaction and what type of product you end up with. So we'll talk about that next time.